Imagine standing in a dimly lit laboratory room, surrounded by humming equipment and blinking lights. I recall pressing my face close to a small observation window, watching researchers adjust delicate lasers aimed at tiny crystal arrays. They worked for hours calibrating instruments that operated at temperatures near absolute zero. On a nearby monitor, graphs and patterns displayed subtle correlations between particles separated by meters, hinting at mysterious connections not explained by everyday experience. Quantum entanglement occurs when two or more particles become linked, so that measuring one instantly affects the other, regardless of the distance between them. Physicists tested this concept many times, starting with early thought experiments like the Einstein-Podolsky-Rosen paradox, and later using more refined setups. Eventually, multiple experiments confirmed that entangled particles display correlations that violate classical understandings of how the world should behave. Over the decades, results repeatedly showed that entanglement is a measurable phenomenon, not just a speculative idea. In 2022, researchers who demonstrated entanglement's genuine effects were recognized with a Nobel Prize in Physics, a formal acknowledgement that entanglement is real and not an illusion caused by experimental flaws. Today, labs routinely create entangled photons and atoms. Systems that exploit entanglement are being engineered to move beyond traditional data encryption and classical computing methods. Particle pairs are carefully generated so that one might remain in a laboratory while its twin particle travels down a fiber optic cable or even sits in a satellite orbiting hundreds of kilometers above Earth. On a calm evening, I once peered through the window of a quantum communication experiment hosted in a small research center. Inside, technicians cooled equipment with liquid nitrogen. Each measured statistic on a screen represented the behavior of entangled particle, showing patterns that hinted at the possibility of eavesdrop-proof communications. Scientists have applied these principles to quantum key distribution, making it far more secure against tampering than classical encryption methods. Although entanglement does not allow faster-than-light signaling, it can serve as a vital resource for confirming security and establishing trust between distant observers. If one imagines an advanced alien civilization, it is possible they could employ entanglement-based communication networks to exchange information without producing radio emissions or detectable signals like those we attempt to find with large radio telescopes. Such networks would leave no conventional electromagnetic footprint. They would be quiet, invisible to our surveys. Large arrays of photon sources, detectors, and quantum memory units might be arranged in orbit around distant stars, passing qubits of data across entangled links that we cannot intercept with current technology. I remember once feeling a small thrill of surprise while reading a scientific report describing the teleportation of quantum states between labs separated by significant distances. The word teleportation sounded like science fiction, yet the document explained it as a confirmed laboratory procedure, or not teleportation of objects, but the state of a particle. Encoded information moved from one place to another using entangled pairs and classical communication channels. This quiet transfer of quantum information occurred with startling fidelity, hinting at future applications beyond our current electronic messaging systems. If alien species have developed sophisticated quantum networks, we would have no direct way of perceiving their data streams. Our radio arrays, optical telescopes, and gravitational wave detectors would find no familiar signals. While we have identified exoplanets and measured their atmospheres, and while we have searched their skies for radio pulses, quantum entanglement communication would remain hidden from these methods. We have learned to identify scattered photons from distant stars, but photons that are part of an entangled pair used by an advanced network would not reveal their purpose to us. Some teams have begun experimenting with quantum repeaters, devices that extend the range of entanglement-based communication by preserving and renewing the delicate quantum states that would otherwise degrade over long distances. Current prototypes can only operate over tens or hundreds of kilometers, but the principle has been established. There are even discussions about placing entanglement-capable devices on orbiting satellites to link distant points on Earth's surface. These steps mark the early stages of building a rudimentary quantum communication web. The methods to generate and harness quantum entanglement are challenging, involving precise alignments, cryogenic temperatures, and fragile components. Over the years, engineering solutions have emerged, including specialized crystals that produce pairs of entangled photons when illuminated by lasers. In cleanroom environments, technicians wearing full-body suits polish optical fibers designed to carry these photons with minimal loss. On tiny semiconductor chips, nanostructures confine single electrons, exploiting their spin states to form controlled entangled pairs. On one occasion, I watched a recorded demonstration where a scientist carefully rotated a polarizing filter as entangled photons passed through. Participants in the workshop reacted with quiet nods and raised eyebrows. They understood the weight of these results. Entanglement is a resource as real and reliable as electricity or magnetism, yet it cannot be reduced to a familiar, everyday image. Without needing to rely on conventional signals, any civilization that masters quantum entanglement could secure its communications from prying eyes. No classic interception method would suffice, since measurement attempts would alter the quantum states, alerting the communicators to the intrusion. The direct consequence would be a system of data exchange that remains private, robust, and invisible using our present monitoring techniques. Some researchers work tirelessly to find new uses for entanglement, including quantum-enhanced sensors that measure gravitational fields or magnetic variations with unprecedented sensitivity. Others focus on scaling up quantum computers that can factor large numbers or simulate complex molecules powered by entangled qubits arranged in stable architectures. Each incremental improvement makes these technologies more practical. In a quiet laboratory corner, I once saw a chilled vacuum chamber with a row of ion traps, tiny electronic devices that suspended charged atoms in midair using electromagnetic fields. Through careful laser manipulation, these trapped ions became entangled qubits, forming the heart of a primitive quantum processor. The team performing these experiments described the challenges. Stray vibrations, temperature fluctuations, and electromagnetic interference all had to be minimized. Achieving stable entanglement required patience, skill, and precise engineering. Entanglement stands as a well-tested phenomenon, confirmed in numerous experiments. Its direct consequences include secure communication protocols, potential quantum computing breakthroughs, and new types of precision measurements. Today, researchers continue to refine these systems, working step by step to integrate entanglement-based methods into practical devices. Each successful test, each new record for distance or fidelity adds to our toolkit of quantum technologies. If extraterrestrial intelligence were out there, relying on entanglement-based communication, we could be surrounded by their information channels without any evidence reaching our instruments. We do not detect hidden quantum keys or entangled photons bearing alien data. This remains a statement of fact. No known method can currently intercept or confirm messages encoded solely via entanglement. The laboratory findings, the Nobel-recognized experiments, and the push towards quantum networks all illustrate that entanglement is real, usable, and offers methods of communication unlike traditional broadcasts. These facts stand, and the potential applications continue to unfold as research advances.